Hi, I'm Mark, and today I'd like to tell you about our new data structure for encoding triangulations of surfaces. Geometry processing is full of algorithms that work perfectly well on the mesh on the left, but produce nonsense on the mesh on the right. Today, I'll show you a new data structure that helps us escape this frustration. The trick is to use integers to efficiently encode a high-quality intrinsic triangulation. Intrinsic triangulations allow us to greatly improve triangle quality while preserving the mesh geometry exactly and not increasing the size too much. All you have to do is allow triangles to bend in certain ways along your surface. The mathematical fundamentals date back to the mid-20th century, but intrinsic triangulations have become increasingly popular in recent years as a simple and efficient approach to robust geometry processing. There are currently two data structures for encoding how these intrinsic triangulations sit over the input mesh. The first option is the overlay mesh, which robustly encodes the correspondence between triangulations, but only supports edge flips. On the other hand, there's the signpost data structure, which supports many mesh operations, but lacks robustness since it encodes correspondence via floating point. We provide the best of both worlds, performing a wide variety of mesh operations robustly. To do so, our data structure builds on the idea of normal coordinates, a robust and concise representation of curves from topology, which has recently begun to see some use in geometry processing. However, in order to use normal coordinates to encode intrinsic triangulations, we had to extend the classical approach in two ways. The first was local mesh operations. Edge flips have been thoroughly explored in the normal coordinates literature, but that's about it. We had to develop new procedures to update our normal coordinates following vertex insertions or removals. The second problem is that when you encode a triangulation with normal coordinates, it can be surprisingly hard to tell which edge is which. To do so, we employed roundabouts, a tool that we introduced earlier this year to perform a similar disambiguation. In this work, we proposed a robust new data structure for intrinsic triangulations, which relies on normal coordinates augmented with roundabouts and supports a variety of local mesh operations. As validation, we implement a recent intrinsic retriangulation algorithm and prove some quality bounds on the resulting triangulations. And finally, we introduce a new procedure to optimally transfer functions between different triangulations of the same surface. Note that our goal here is not to introduce new applications or algorithms of intrinsic triangulations. Rather, we provide a new data structure that supports all of the existing applications and algorithms, but performs far more robustly due to its greatly reduced dependence on floating point. Now, let's briefly discuss what normal coordinates are and how they work. Normal coordinates allow us to encode a straightest path along a mesh by simply counting how many times it crosses each edge. Say we count these crossings and then forget our curve. Now, there are a bunch of curves on the surface that all cross these edges the correct number of times. But if we take the option that bends the least, we always get our original curve back. This still works even if your curve is pretty complicated. We can forget about the curve and then recover it exactly from the crossing counts. The key takeaway here is that you can encode a straightest path exactly using only integers. And it even works for collections of curves. Taking this to an extreme, we can store an entire intrinsic triangulation via normal coordinates using just one integer per edge. Now let's discuss some applications. Using our data structure, we can implement a recent retriangulation scheme computing high-quality intrinsic triangulations of low-quality meshes. Here, our data structure acts as a drop-in replacement for the signpost data structure. To validate our integer coordinates, we computed intrinsic retriangulations and verified the correspondence on all of the manifold meshes in Thingy 10K. Retriangulation was quite fast, taking less than a second on most meshes, and we successfully obtained high-quality triangulations and valid correspondence on all meshes. For comparison, signposts succeed on only 70% of meshes. For algorithms like the heat method, which are sensitive to triangle quality, these triangulation improvements can dramatically improve your solution quality. We also introduce a procedure to transfer such solutions from the intrinsic mesh to the input mesh optimally. This sort of procedure has been widely explored in the extrinsic FEM literature, but had never been done before in the intrinsic setting. And this can greatly reduce error. For this Poisson problem, finding the closest function on the input mesh yields a much more accurate solution than the naive method of copying values of vertices. Finally, let's discuss some limitations and future work. One interesting direction would be to develop a hybrid data structure that maintains both signposts and integer coordinates. Signposts perform several operations more efficiently than integer coordinates, and a combination may be able to offer the robustness of our approach combined with the efficiency of signposts. Another interesting extension would be to construct a truly integer-only encoding of intrinsic triangulations. While we greatly reduce the use of floating point, we still use it to store edge lengths, but you could, in principle, compute these edge lengths as needed from the normal coordinates. Speaking more generally, we inherit the usual trade-offs of intrinsic triangulations. In particular, we exactly preserve the geometry of the input mesh, which means that we cannot coarsen the mesh and we cannot repair spurious holes and handles. Finally, although I focused entirely on normal coordinates for curves today, this concept was originally developed to study surfaces embedded inside of tetrahedral meshes, so it would be interesting to consider higher dimensional applications. Thanks for listening.